All right, so as promised, I'm going to try to walk you through Virtual Fly Lab 2. It's a little more in depth than the first one. Everybody did a good job on the first one. And this one's very similar to, so what we're trying to do in this one, the big picture, is we want to look at some genes that by themselves have different inheritance patterns. So when you do just mutant A by itself, you might get something different than 3-to-1 ratio. And then mutant 2, you might get a 3-to-1 ratio or something else. And then when we combine these things together, we should be able to predict what these ratios are going to be in a dihybrid cross. And so you have to keep an eye out for some different inheritance patterns, and then keep that in mind as you go through the crosses. So I'm going to go back. So this is the Virtual Fly Lab site, but I'm going to go back to the course web and show you where to get the mutants. So I'm actually going to basically wing it and not show you, not follow the instructions exactly. But I think I know what they are. But first I'm going to go get my mutants. So I'm going to use mutant list 1. Everybody else should have their own mutant list. And if I look up here, I might have to write these down. All right, so what do we got? Mutant list 1. Ebony, Star, and Forked. Okay, so that's not too bad. So there's only 3. Ebony, Star, and Forked. And I'm going to grab a piece of paper. And so for the each of these genes, the first step is going to be to figure out what these genes are doing by themselves, and then use that information to predict what would happen if we cross them together. So I've got my mutants, so I won't need this anymore. And we'll go over here and we'll start with Ebony. Sometimes this takes a while to load up. So there's that. And I'm going to open up a Word document, and I'm going to keep rather than just using the Virtual Fly Lab sheet, I'm just going to keep my own little notebook here. You're welcome to do that too if you like, as long as you just do everything. So cross 1, we're going to take Ebony female cross to a wild type male. All right. And it's important to use the mutant female and cross it to wild type male in the first cross, because that will immediately show you if there's sex linkage. So hopefully you've looked through some of the sex linkage stuff in chapter 4. And when we get to one that's sex linked, I'll point out what those patterns are. So cross 1 will be an ebony female cross to a wild type male, and then we'll do the F1 cross as well. So let's go check this out. And I'm going to turn off my options. So if you haven't figured this part out yet, you can turn off these options, and that just speeds things up. It speeds things up, and it gets rid of the annoying noises. And then you go over to activity and just do this crosses the same way. We order some flies. I order my female. We said it was body color. We're going to do ebony. And notice that black, ebony, and sable all have black bodies, but those are all different genes, and they're all on different chromosomes. So I'm going to add that female to the cart. I'm going to grab a male, make him wild type, add him to the cart, order them, check out. Yep, I really want to check out. Unpack my flies. It's a lot faster if you do it this way. Put those guys in the incubator. Open it up. Sort them. And then I got all wild type. All right. And notice I've got my males and females are all wild type. There's no difference between males and females. So at this point, there's no evidence for sex linkage. It turns out that if they were sex linked, at this point, the males would all be mutant. If you use a mutant female crossed to a wild type male, then you'll see that all of the males are mutant. And we'll see that one of these is going to be sex-linked, so we'll see what that looks like. But now let's look at the F1. So we'll put herd in new mating, zoom out, use him in a new mating, zoom out, return to lab, put those guys in there. Notice how the time goes by really quickly. Check these out, sort them. Here's my data. Let's send that to the computer. Analyze the results. Because we know it's not sex-linked, or even sometimes the sex linkage, depending on how you set up the cross, doesn't show up to the second generation. So you still have to kind of keep an eye out for it. But notice here our males and females that are wild type are pretty much the same. And the males and females that are ebony are about the same. So we're not seeing a difference in sex linkage at this point. So we can pretty much assume, or we don't really assume, we conclude from this cross, if it was sex-linked, it would show up by now. Sex linkage will always show up in either the first generation or the second generation, depending on how you set up the cross. So we can ignore the sex. That makes life simpler. We can do a chi-square. Looks like, this is ebony, so it just kind of looks like a 3-to-1. Got a high level of significance. We do not reject our hypothesis. So ebony looks like it's a normal non-sex-linked gene. So I'm not going to put all those results in here. You guys, cut out your results and put them in. But we can just say F1, we're all wild type. F2 showed 3-to-1 ratio. No differences between sexes. Conclusion: ebony is a recessive mutation. So when I say recessive, I mean recessive to wild type. And it's not sex-linked. So not sex-linked means it's autosomal. So this is an autosomal recessive mutation. Or a mutation. It's a mutation or a mutation. So it's a mutation. All right, so I'm going to save this. I'm going to save this. Save it as my VFL2 notebook. So I recommend that you just kind of keep a notebook, and you can copy and paste in your results. Maybe I should do that. If I go back here, maybe I want these results. And I'm using my surface, and the snipping tool is. Oh wait, hold on a second. I found it. So I might as well put my results in there somewhere. Grab these, and this is usually basically all the results you need. The second cross, well, whatever you need the results that are important. So we can just right now I'm just putting those in my notebook. If I wanted to put them in a different order in an assignment, I could come and grab stuff from here. So it's good to keep a notebook as you go, sort of a little electronic notebook. All right, so what do we do now? Let's go back to the cross. So that's ebony. So ebony is an autosomal recessive mutation. Okay, nothing new, nothing too exciting. Let's go back. And now what we want to do is get rid of those flies, because it gets confusing, and then we actually kind of run out of room at some point. So go to the computer, order some new flies. My second mutation was star. So let's do star. We'll make a star female. And I think that's eye shape. Yep, there's star. See how there's kind of little ridges around the eyes, so they're star-shaped eyes. Add that to the cart. Our male is going to be wild type. Add him to the cart. Check out. Yep, really want to check out. Put my flies in the incubator. Let them mate for a quick 14 days. Grab them. Sort them. Okay, so now this is where it gets confusing, and I think all of you have seen this already. If you've tried this, you've seen this now. So now we've got everything else we've done so far in the F1, everything's been the same. Now we've got the F1 where we've got two different things. So what's going on? So the first thing to think about is it sex linked? Males and females. So I'm going to send the data to the computer just to make it easier to analyze. So male and male star and male wild type, female wild type. So if we compare the female wild type to the male wild type, they're both 280 something. Males and females, there's a slight difference, 321 over 276, but it's, for the most part, they're showing the same general pattern. So it doesn't look like males and females are showing a majorly different thing. So we can ignore sex. So now what we have is 1-to-1 star to wild type. All right, so let's analyze that a little bit. Let's go down to cross 2. Star female cross to wild type male. And we got 1 star to 1 wild type. So we have a 1-to-1 ratio. What does that look like? So it's a good idea to have a general idea of the various kinds of ratios that show up. We've heard of a 1 to 2-to-1. We've heard of a 3-to-1. We've heard of 1-to-1. We've heard of a 2/3 to 1/3. And this looks like a 1-to-1. And 1-to-1 is characteristic of a test cross. And so a test cross of a heterozygote. What does that mean? So we got big A cross to, we got big A, little a, cross to little a, little a. That gives us 1 big A to 1 little a, little a. All right, so maybe that's what's going on. If that's the case, then one of our flies is heterozygous and shows the dominant phenotype, and one of our flies is homozygous recessive. Now, I told you that with this program that the rules are that the wild type flies are always going to be homozygous if they can be. So that means that these guys are going to be the wild types. So we have our star female cross to wild type male, and we know that the male is this. So that means that this female has to be this. And let me just caution you that because even though I'm using the words male and female, we're not doing any X linkage here. So there's no reason to start adding in X and Y chromosomes. We showed in the first cross where the female crossed to the male, we saw no difference in the sex, or in the phenotypes of the sexes. There was no, so sex linked means that one of the phenotypes kind of is linked to the sex. That means that all the males are going to have that particular sex, is usually what it means. Sometimes all the females. So anyways, so what this looks like is is this kind of that the original cross was this kind of a test cross. And I told you that all the mutants would be heterozygous if they, or homozygous if they could be. But this one is heterozygous. So that means that it can't be homozygous. Right? So keep that in mind. And so now we want to do our F1 cross, and we want to make sure that our F1 cross is a monohybrid cross. We want to use the heterozygotes. So in the instructions it says, for this cross, make sure you use a heterozygote. If you don't, you're going to lose points and all that kind of stuff. That's just because I really want to emphasize, because what everybody does is they just take this male and female and cross it again. So we did this cross, big A, little a, cross to little a, and then we get this out. Sorry, this should be little a. And so then we get this out. And then what people do is just take these males and females and cross them back together. But that is just redoing the same cross again, and it doesn't really add anything to the situation. So what we want to do is take two of these, two of the heterozygotes, and both of those are going to be star. So now we're going to take a star female and cross to a star male. Now you guys might have curly or stubble or Aristopedia. There's lots of different mutants that show this particular phenotype. And so what do we know at this point? We know that this mutation star is dominant because our original fly that we bought had to be heterozygous because of the inheritance pattern, and it was heterozygous and it showed the mutant phenotype. If it's heterozygous and shows the mutant phenotype, that's the definition of dominance. Definition of dominance is you take a heterozygote and whatever shows up, that's the dominant thing. So if wild type shows up, wild type's dominant. If the mutant shows up, the mutant's dominant. All right, so we're going to take star female and cross it to a star male and see what we get. Now these are the F1s. Now we could actually buy them again if we wanted to, because we now know that all these, when we buy them from the store, they all have to be heterozygous. But let's go and we'll just cross these guys. So here's our F1s. Is that our F1s? Yep, so that's our F1s. So now, but now we got 4 different things. So we have to make sure, we want to make sure that we pick a female star. Use that in a new mating. Zoom out. What's that? That's a male star. This is a wild type female. This is a wild type male. We don't want to use these. Well, we don't want to use a female because we already used a female. And if you put 2 females in there, you're not going to get any babies. We want to use star because we know that that one's heterozygous. And we want to do a monohybrid cross because that's going to give us more information. So grab that guy, use them in new mating. Okay. Zoom out. Turn to the lab. We got our new mating thing, which is 2 stars mated together. And both these stars are the F1, and we suspect that they're heterozygous. Sort them. Return to the lab. Oh, I didn't want to return to the lab. Hopefully the same guys are in there. We want to send the data to the computer. Analyze results. We already know that it's not sex-linked because we showed that in the first cross, so we can ignore sex. And now what do we got? We got 781 to 400. All right, now, and we know this is a monohybrid cross. We crossed 2 monohybrids together, 2 heterozygotes. So let's do a chi-square analysis. So if it's a monohybrid cross, we might expect it to be a 3-to-1 ratio. If we do this, we get a level of significance of 0 and a chi-squared of 49. So that's a super huge chi-square statistic. And remember, so what chi-square measures, what it's essentially measuring is the difference between the expected and the observed. So this is what we expect. If we count up about 1,200 flies, we expect, based on a 3-to-1 ratio, we expect 885 of these, 295 of these. We're not getting that at all. We're getting 781 to 400. And so this is a big difference between E and O. And that gets reflected in a big chi-square value. And then when you use a chi-square table with 1 degree of freedom and all this kind of stuff, you end up with what's this level of significance. And so this level of significance is what's the probability that this difference that we see between the expected and the observed, is that a significant difference? And so what the level of significance is, that's the probability. It's actually what the probability that difference is due to chance. And the probability that it's due to chance is 0. So that means it's not due to chance. That means it's due to something else. All right, so that means we reject the hypothesis. So we should probably keep this data. Seems like some pretty good data. It's kind of fun. We get to do experiments without waiting 2 weeks between crosses. It's kind of a pain in the neck to do that. But when you're dealing with real organisms, that's how it goes. All right, so we get this. And what do we conclude from that? We reject the 3-to-1 hypothesis. All right, so why is that? So remember, I told you that these flies would be homozygous if they could be. So in this case, star cannot be homozygous, and they die when they're homozygous. So that means it's a lethal allele. And so that means that it's going to show the inheritance pattern of a lethal allele. And if you look at chapter 5, the first part of chapter 5, section 5.1, it talks about some lethal alleles. And the characteristic inheritance pattern for lethal alleles is 2-to-1 instead of 3-to-1. So let's test that. That looks good. So now we got a low chi-square value and a high level of significance, way over 0.05. So that means that we accept our hypothesis that this is a 2-to-1 ratio and that it's a lethal allele. All right, so we accept that hypothesis. So now what we're saying is when we take star, cross to star, we get 2 star, oops, not at star, 2 star to 1 wild type. And we know that these guys were both, well, I don't know if we know it, but we suspected that it was a monohybrid cross. Monohybrid crosses, here's always my secret to get more out of it. I always make my margins narrow. I'm going to get more room. That's why none of your exams ever have any margins on them. So 1 like this, 2 like this, and 1 like this. So we know that the 2 are heterozygous, and we know that the 2 in our 2-to-1 ratio was star. So that means the heterozygotes are star, and that means star is dominant. And if star is dominant, then 2 little a's is wild type, and wild type is recessive. And the idea is that we don't get these. Anyways, I was going to look for straight through and get rid of those. These guys die. Because the big A is a lethal allele. We could use A. We could use ST, which is the official star designation, at least in this program. And so anyways, so that's what we get. So it's a lethal allele. And so that means anytime we do a monohybrid cross with star, we expect a 2/3 to 1/3 ratio. So later, when we do star and another cross to something else, we have to factor in this 2/3 to 1/3 ratio when we try to figure out our dihybrid thing. So if it was 2 normal genes, we'd expect 3/4 to 1/4, 3/4 to 1/4. We multiply those guys together, we get 9 to 3 to 3 to 1. In this case, when we do that cross, we'll just do that one next to keep it, kind of keep the flow going. Our new prediction will be 2/3 to 1/3 for star and 3/4 to 1/4 for the other thing. All right, so let's do that. So our next cross, so this is where it's important to do the prediction ahead of time. So our next cross is going to be star cross to ebony, because that was our other thing. You are welcome to do, we could also do star ebony cross to wild type, and that would give you the same thing. But we'll do star cross to ebony. Now we know both of them are not sex linked, and so it doesn't really matter if we use which one's a male and which one's a female. But we'll do it this way just because this is kind of makes it, this is a little bit more complicated when it comes time to figure out where the where the genes are coming from. And not that more complicated is good, but it's good to see the example of the more complicated one, just because if you see that the more complicated one later, then it's better. So what do we expect? Well, we know that star is going to be heterozygous. And the thing that's tricky with these things is this star female is wild type for ebony. So let's So we can still use A. Let's use, what do you want to use? Everybody raise their hand. Let's vote for, we'll use E. E is the official ebony thing. So this star is wild type for, is wild type for ebony, and we know that ebony is recessive because we did that in the previous cross. Now this is an ebony male, and we know ebony is recessive, so he has to be homozygous recessive. And we want to keep the genes in order. So if we've got the A on the left, we want to keep the A on the left. And this ebony male is wild type for star, and we know that star is recessive, so it gets that. You can use S's, you can use STs. What we would actually use in real, if you were really doing some Drosophila genetics, we actually end up using pluses for wild type all the time. And I found over the years that gets really confusing for students, and sort of introduce these different concepts and introduce different terminology and symbolism at the same time. It makes it a little crazy. All right, so we got this thing. So we got a star female and an ebony male. So what do we expect? Well, we expect for ebony, well, let's do star first. So for star, we expect 1 this and 1 this. So for you just star, we expect a 1-to-1 ratio of this. And for ebony, we expect all to be this. So when we do this cross, we're going to get this is wild type. We're going to get 1-to-1 star to wild type. But and this is going to be in the F1. So, so this is the parent cross that we're going to set up. This is the F1 cross that we're going to set up. But then we want to do a dihybrid cross. And so we're going to want to take the ones that are star because they're going to be heterozygous for both things. So our F1 cross, we want it to be a dihybrid cross because that we can predict. And so that means the phenotype of these are going to be star, and these are going to be star. And we'll take 1 male and 1 female. So what do we expect in the F2? Well, it's a dihybrid cross. You might think, rightfully so, if you jump to conclusions, that, well, not rightfully so, but justifiably so, you'd expect 933-1. Yeah, it's a dihybrid cross. Dihybrid crosses give you 933-1. Well, that's high school genetics. Time to move on. What we know is we're going to get 2/3 star in 1/3 wild type. We also know we're going to get 3/4 wild type sorry about this, try to get this 1/4 ebony. All right, so then how many are going to be just star and wild type for ebony? How many are going to be, let's say, star and ebony? These are just we're going to have 4 possibilities like always. Some will be just wild type. And some will be just ebony. So what are the genotypes of these guys? Well, we know star is, if we do it, let's see. Yeah, so, well, we know star has to be big A, little a. And if it's ebony, or if it's wild type for ebony, it's going to have a big E and something else. Star and ebony, we know it's going to be big A, little a for star, because we can't get big A, because they die. So if it's star, it has to be big A, little a. Ebony's little e, little e. Wild type for star is recessive, or star's dominant wild type is recessive, so we get that. And if it's ebony, if it's wild type for ebony as well, then it's that. And if it's just ebony, we know it's wild type for star, mutant for ebony. So those are the genotypes. Not the most straightforward thing in the world, but we're just thinking about the whole key to this process is to think about each gene by itself. So what's star doing? What's ebony doing? What does that depend on? That depends on independent assortment. So we're saying that the inheritance of one gene doesn't affect the inheritance of the other gene. So that depends on independent assortment. And it also depends on the fact that the star isn't influencing ebony and ebony isn't influencing star, sort of at the molecular level. So we'll come to that. That's called epistasis or gene interaction. And sometimes even if you have independent assortment, you get messed up ratios. But we'll come to that later. So star and wild type. Well, 2/3 star, 3/4 wild type. You can barely see that, but that's 2 times 3 is 6. So that's 6/12. Which is also 1/2. Star and ebony, 2/3 star, 1/4 ebony. That's 2/12. 2/12 star and ebony. Wild type for both is 1/3 wild type for star, 3/4 wild type for ebony. That's 1/3 times 3/4. That's 3/12. And 1/3 times 1/4 is another 1/12, and that's just ebony. Now it's always worthwhile to add these up. So 6/12 is, and these are of the flies that live. So we can only count the flies that live. If you were to do a Punnett square, you would go in there and you would cross out anything that has big A, and you would get rid of those. And so that's kind of what happens. But we also need to make sure that we've accounted for everything. So we got 6 plus 2 is 8, plus 3 is 11, plus 1 is 12. Look, I did that even without a calculator. So if we add it up, it's 12/12. So that's what we expect. All right, let's go test that hypothesis. And all we did was, so far, is look at the predicted ratios based on what each gene is going to do by itself, and then multiply them together. And that depends on independent assortment. It's certainly possible that these genes could also be linked. If they're linked, so basically what we just showed is that's our hypothesis. If one gene is showing a 2-to-3 or 2-to-1 ratio characteristic of a lethal allele, and the other gene is showing a 3/4 ratio characteristic of just a normal monohybrid cross, and we multiply them together. The multiplying them together part, that depends on independent assortment, because that's the law of probability if two events are independent. And if the genes are on different chromosomes, they are inherited independently, and so that's what we mean by independent assortment. If they're linked, it screws everything up, and you wouldn't be able to really analyze it very easily. All right, so let's order some flies. We're going to make a star female. See how fast we can do this. I shape. Star. Add her to the cart. Body color. Ebony. If you want to check it out, if you want to play around with this, try it with black. Try it with sable. Life will get more complicated. Because they're on different chromosomes that behave differently. Got everybody? Sounds good. Unpack them. Toss them in there. That was a fast 2 weeks. I hope the weeks don't go past that quickly this summer. Sort some flies. What do we got? So remember we said we were going to get 50-50. All right, so that's what we expect. Star is just behaving the way it's supposed to, but all of these flies are heterozygous for ebony. Right? Because the star fly was wild type for ebony, the ebony fly was homozygous mutant, so all of these are heterozygous for ebony. So let's take a male, or a female, sorry. And she's star. Use her in a new mating. Okay. Zoom out. So this is kind of the critical part. We want to use a star male. So there's a wild type male. If we use a wild type male, we're sort of taking star out of the equation. because now star is homozygous wild type, and all we'll see is ebony coming back out, and we would actually it would just kind of mess it up. So it's not going to be a dihybrid cross. So we want it to be a dihybrid cross. So what do we need? We used a female, right? So we need a male. Use a new mating. I'm not sure what happens if you try to put two females in there. You can play around with that if you want. I think I might need to return to the lab. Yep, and so there's our star female, male. Now these guys are heterozygous for star and ebony now. Sort them out. Send the data to the computer. Analyze results. Ignore sex because we know they're not sex linked. All right, now this is a dihybrid cross. So just for the fun of it, let's try a 9 to 3 to 3 to 1. Zero probability that this difference is due to chance. So that's a zero probability that we accept this hypothesis. 51 is a super humongous chi-square value. That means there's a super humongous difference between what we expect and what we observed. Even though we observed 592 and we expected 666, that doesn't seem like that big of a deal, but apparently statistically it's a huge difference. All right, so let's enter a new hypothesis. I barely remember what it was. I think it was 6/12 to 3/12. You can kind of tell it's 6 to 3 to 2 to 1. So it's the infamous 6 to 3 to 2 to 1 ratio. Lo behold, this is what we get. Very low chi-square statistic. Remember the last one was like 55? This one is super low, and our p-value, or our level of significance, is super high. Remember, the highest you can get is 1. So this is the probability that the difference that we see between observed and expected is due to chance. That probability is in the 88% range. That's super high. So the lo behold thing, that's from my biochemistry professor, Dr. Chan, way back at Syracuse when I was there as a graduate student. He had two sayings. One, when he would come to some conclusion like this, he'd say, lo behold, and this is what you get. And I still remember that. And the other one is, couldn't be simpler. So he'd like go through the entire Krebs cycle in excruciating detail and then say, couldn't be simpler. And I always thought, it probably could be a little simpler. But he was a great guy. He did a lot of cool stuff. And maybe I'll tell you some more Dr. Chan stories later. All right, so we're accepting that hypothesis. I'm digging it. So let's grab that. Awesome hypothesis. Tested it out. Life is good. Now, a lot of times students get like sort of emotionally attached to their hypotheses and feel bad if their hypothesis gets rejected. That's the way science is. If you're doing real experiments, trying to figure something out, a lot of times the best thing you could have happen is to reject your hypothesis. For example, if you're testing a drug and you're testing a drug against a placebo, and if there's a significant difference between the drug and the placebo, you're going to make $1 billion. But so you do an experiment, you do a statistical test, and the null hypothesis is that there's no difference between the drug and the placebo. And then you do your statistical test, and it says, "Why, yes, there is a significant difference between the drug and the placebo. So I'm going to reject the hypothesis that there is no difference." It's kind of weird, backward statistics logic, but you reject the hypothesis that there is no difference. Well, if you're trying to make this drug, you want to reject the null hypothesis that there is no difference. If there's no difference, you're not making any money. But what we're doing is we're just trying to find which model the data fit best. Does it fit 9 to 3 to 3 to 1? Does it fit 6 to 3 to 2 to 1? Which one does it fit? So in this case, it fit 6 to 3 to 2 to 1. All right, so we're good to go. And so what do we conclude? Star is dominant. Star is lethal when homozygous. Just to confuse things, that means it's a recessive lethal because it's recessive for lethality, but it's dominant for eye shape. so that's weird. Ebony is a recessive autosomal. They're both autosomal, and ebony is a recessive autosomal. Autosomal means non-sex linked gene. When we do a dihybrid cross between them, we see the weirdness that the star brings to the table, giving us, which throws off the 9:3 to 3:1 ratio, but it gives us the 6:3 to 2:1 that we predict if there's independent assortment. So in other words, the only weirdness that's going on is that there's this lethal allele that gives us a 2:1 ratio, and that screws up our 9:3 to 3:1 ratio. But independent assortment is still occurring. VFL3 is where we start to say, whoops, look, there's no independent assortment. Just a little hint. As soon as, and that means genes are linked, and when genes are linked, we do test crosses, because I can't remember if VFL3 has you do a dihybrid cross, but if you do a dihybrid cross with linked genes, it's crazy. When I do the VFL3 video, I'll show you that. All right, so that's cool. So we just did ebony and star, figured out what's going on with ebony and star. Okay, so now what are we going to do? Let's do forked. And we'll get rid of all these guys. And we'll do forked. Take our female. Forked is a bristle thing. Where's my bristles? Forked. And that's kind of what they look like. They're actually literally forked. There's like a little, I don't know, split. But split's a different mutant. There's lots of bristle mutants. Add that to the cart. Males, wild type. Add that to the cart. Check out. Yep. Unpack them. See what we get. Oh, I kind of like seeing the paintbrush. All right, now what do we get? So now, so we took a mutant female, a forked mutant female. Cross that to wild type male. In the F1, we get all our females are wild type, all our males are forked. All right, so this is our new cross. So whatever cross this is, I think this might be cross 3. So we took a forked female, crossed to a wild type male, and we got 1/2 of our flies were wild type females, and 1/2 were forked males. Conclude. Forked is X-linked. You could also say sex-linked, but X-linked is more descriptive. Okay, so what does that mean? Now, this is hard to do on... I don't have my good pen to draw things, so I kind of have to do it. But just typing makes it hard to do X-linked things. So you'll have to bear with me. It's kind of a pain in the ass, but we'll do it. So if it's X-linked, that means our females have 2 X chromosomes crossed to a male that's X and Y. Characteristic of an X-linked trait. And nope, this is forked, sorry. That means that I have to make that thing superscripted. This is so much easier to do when you can write it down. But it's not horrible. Oh, it's kind of horrible. All right, let's see. So how do I do superscript? All right, I want to get in there. All right. So now that's XF. I'm going to boost those up a little bit so we can see what the hell we're doing. Oops. All right. And then now we can just copy this XF. So just bear with me. So our female is X to the F power. That's not really what it means. It just means that's the X chromosome within the forked allele is on the X chromosome. For this, I'm going to go ahead and use this designation, just because it gets hard to see the difference between a little f and a big F. So we're going to say the wild type allele for the forked locus is plus. Okay. Now, if we cross these two, what do we get? Well, we can get, this part makes it kind of cool. So we can get that from mom. All right. So we can get that X from mom. And we can get this X, well, not that X, but this X from dad. And forked is recessive. This inheritance pattern is characteristic of X-linked recessiveness. So what I'm doing there, I'm right-clicking on that thing, and then it goes to font, and then you have the option of doing superscript in case you don't know how to do that. So that's one of our offspring, and that's a wild type female. The males can get this X chromosome from mom. But they have to get a Y from dad. All right, very good. And that's a forked male. So the pattern for X-linked recessive is mutant mothers, or mutant, yeah, it could be mothers, mutant females, pass the trait to all of their sons. And we'll see the same thing in pedigrees. If you have a mom that is homozygous for the color blindness allele, which is kind of rare, but let's pretend she has that. All of her sons have to get her X chromosome, and they get a Y from dad, and they'll all be colorblind. All right, so that's it. So that tells us that that the fact that we saw this difference between males and females, that tells us that this is a X-linked recessive. Now we could do X-linked dominant, but we're not going to do that for now. X-linked recessive is our only option at this point. Well, it's not our only option, but that's characteristic of X-linked recessive. The other thing that's characteristic of X-linked recessive is that if you do the cross the other way, you get a different result. So we'll do that in a minute. So now we can take these females. So we can take these females. So I want to take those females and cross them to their brothers. What do we expect? We expect to get this X from mom and this X from dad. We can get this X from mom and a Y from dad. Get this X from mom. Feel free to do a Punnett square if you like that better. Get this X from dad. Get this X from mom. Get this Y from dad. And what do we got? this mom, or this daughter, is forked. I think maybe if I paste that in, it'll come in as forked. So that's a forked female. That's a forked male. That's a wild type female. Where'd the other dude go? And this is a wild type male. And so this is the F1 cross. And this is our F2. Now you'll notice at this point it's one of these, one of these, one of these, and one of these. So there's no difference between males and females in the F2 generation when you do the cross this way. But there's a difference here. The males and females are different. So now let's test this. So now we're going to go back and grab our forked males and our wild type females, cross them together, and see if that's what we get. There's our wild type female using new mating. Zoom out. Forked male using new mating. Okay. Zoom out. Turn to lab. Toss them in there. Wait 2 weeks. Check them out. Now, before we sort them, what do we expect? Well, we just crossed a forked male, so he has to have the forked allele on his X chromosome, and a wild type female who is heterozygous, and we just showed that we expect 1 to 1 to 1 to 1. Sort flies. Oh, what happened? Here we get basically 1 to 1 to 1 to 1 of forked females, forked males, wild type females, wild type males. Send data to the computer. At this, now even at this level, even though it's sex linked, we can ignore sex because they're the same. And so we basically just get half forked and half wild type, regardless of sex. All right, sounds good to me. So that's just the sex-linked pattern of inheritance. And so that's just what we watched. So we took a homozygous forked female crossed to a wild-type male, and then we get all the males are forked and all the females are wild-type, and that's the difference. Okay? So now I'm not going to write it all down because that's kind of a pain. But I'm going to show you what happens if you do the other thing. So let's toss these guys away. And now let's do the cross the other way. So we just used a female that was forked. Now let's use a female that's wild type and make a male that's forked. Nope, that male's supposed to be... So I don't want to do it. I'll just empty the card. Yeah. I can live with it. All right, wild type female, male. I want my male to be forked. Why wasn't my male forked? Female wild type. So what do we have in there? Yeah, okay, there we go. Male forked, female wild type. All right, good. Check out. Check out the cross. So what do you think? Sort the flies. They're all wild type. So now we don't see a difference in the F1. So let's go back here. So what the hell are we doing now? We're doing now we took a wild type female, cross to a forked male, and we got all wild type, regardless of sex. So this is called a reciprocal cross. If genes are sex linked, the reciprocal crosses will give different results. So if we took ebony female cross to wild type, we're going to get all wild type 3-to-1 ratio. If we switch it around and use a wild type female and an ebony male, all wild type 3-to-1 ratio. So if it's an autosomal gene, it doesn't matter which one you use as a female, which one you use as a male. If it's sex linked, it matters which one you use as a female and as a male. And by doing the cross in a different way, that's called the reciprocal cross. And so we would expect a different thing. And what did we get? We got that. So now, if we take these guys together, take the F1, wild type female cross to wild type male, what do we get? What do we expect? I'm going to let you put those genotypes in so we know, because I don't feel like typing them all in. So if you just put in here the X plus XFY, wild types, and just follow the chromosomes through. But I want to show you that you get a different result. And now what I want to do is I'm going to cross these F1s. So my two wild types, these are the F1s of that cross. Analyze it, sort them, send the data to the computer, yes. So now what do we get? Now I've got wild type females, but half of my males are forked and half of my males are wild type. So one way to say this is 1/2 of the females are wild type. 1/4 of the flies are, so 1/2 of the flies are wild type female. 1/4 of the flies are forked males. 1/4 of the flies are wild type males. So we see a difference between the females and the males. So that's indicative of sex linkage. In this case, we notice that this difference in the F2. So you'll notice the difference in the F1 or the F2 depending on how you do the crosses. And that's why it's always good to start out using a female that's mutant and cross that to a wild type male, because if it's sex linked, you see it right away. You see it in the F1. All right, and I've been curious if we try to ignore sex. No, I guess you can ignore sex, but it obscures the results. It's because so in this case, if you see a difference between the sexes, you need to keep that in mind. All righty. So now let's combine a couple of these things. So now because you have to combine all different combos, right? So we did star and ebony. Let's do forked and ebony. All right. Get rid of those guys. Order some flies. Now we're going to do forked to ebony. Forked to ebony. Let's do it the hard way. So let's make our female. Well, we can do it in a couple ways. All right, we'll make our female ebony. We'll make our male forked. Now we know that forked is sex linked, and we know that ebony is autosomal, so we know what to expect. Send them to the cart. Check out. Yep. So all wild type. That's not too surprising. Because if we look at this fly, we took a female ebony crossed to a male that was forked. Ebony is just an autosomal recessive, so if we cross ebony to wild type, so this male is wild type for ebony. So so for the ebony gene, we're just crossing ebony to wild type. That's going to give us all wild type. For forked, the female is wild type for forked. The male is forked. We mate them, and they're going to be all wild type. That's what we saw in the last generation. All right, so now let's mate these guys. So now we're going to take this female, using a new mating. Use that male, use a new mating. Zoom out. Why can't I send my data to the computer? Oh, I gotta go back and check out my mating. So those are the F1s. We're gonna mate them. And I'm not going to sort those yet. Let's go back and predict what we're going to get. All right, so what did we do? We took an ebony female crossed to a forked male. We got all wild type. Well, let's do the easy one first. We know that ebony is heterozygous, because this female was ebony. And the male for ebony was wild type. This female, and we always keep the X chromosome on the left. The female is wild type. I'm not going to do the superscript this time because it'll take too long. So, the female is wild type. The male, I don't like it. All right, I'll do the superscript. Okay, ignore whatever that wants me to ignore. I'm just going to get that little guy, right click it, go to font, superscript. There's an easier way to do it, but that's even more confusing. So we might as well superscript everything, so we can copy and paste. So now we got that. All right, that's cool. So that's our parent cross, our F1s. Got an X chromosome from mom, X chromosome from dad. And so that's the female, wild type. Heterozygous for forked, heterozygous for ebony. The male got this X chromosome from mom, and got this Y from dad, and he's also heterozygous for ebony. If we cross this, we just showed that we expect half the flies to be wild type females. We expect 1/4 of the flies to be wild type males. We expect 1/4 of the flies to be forked males. All right, so where did I get all that? That's what we got when we did the cross this way. When we did the reciprocal cross, what happened? Didn't I type that in there before? Well, anyways, I thought I had typed that in. But when you do this cross this way, so if you use a wild type for ebony female and a forked male, you expect all the F1 to be wild type, and then in the next generation, you're going to get all your females. All your females have to get this X chromosome from dad, so they're all the females are wild type. The males can get either this X chromosome from mom or this X chromosome from mom, and so wild type female, they all get this. And then they can get either this or all right, so I can get those two things. Your males can get either one of these X chromosomes from mom. So you can get that, or they can get this. If they get that, they get a Y. Or they can get this. And if they're males, they have to get a Y from there. All right, so that's what we get if we had ebony times that. So that's what's going on with forked. What's going on with ebony? Ebony's straightforward, 3/4 wild type. One-fourth ebony. So what do we expect out of this cross? We expect 1/2 to be wild type females. So we're going to expect 1/2 times 3/4 to be females that are wild type for both. So that's wild type for forked, wild type for ebony. We need half to be, so then we're going to take 1/2 wild type females across to 1/4 ebony is going to be 1/2 times 1/4. These are wild type females that are also ebony. We're going to have 1/4 times 3/4 that are wild type males that are also wild type for ebony. So they're just going to be wild type for both. I'm going to move this down so we can move all at the same time. It's a lot easier if you draw it out. I'm sorry, I forgot my pen, but this is what we expect in the F2. So we're just saying 1/2 are wild type females, 1/2 are females that are wild type for forked, times 3/4 wild type for ebony. 1/2 times 3/4. 1/2 times 1/4. 1/4 times 3/4. 1/4 times 1/4. Then we're going to have another one, 1/4 times 3/4. 1/4 times 1/4. It's a little confusing. It's hard to do showing this. So this 1/4 times 1/4 was wild type males. So the first 1/4 times 3/4 was wild type for both. 1/4 times 1/4 is our males that are ebony. 1/4 times 3/4 down here. So now we're going to take forked males. So take males that are forked but wild type for ebony. And 1/4 times 1/4 that are males that are forked and ebony. So we put all that together. We expect 3/8 wild type females. 1/8 ebony females. 3/16. Is that right? No, that's, wait a minute. Yep, 3/16 are wild type males. 1/16 are ebony males. 3/16 are forked males. And 1/16 are forked ebony males. Okay, so this is if we did the cross in, all right, so this is what we're predicting. So we did the cross the hard way. We did the cross so that we don't see the results until the second generation. So we crossed ebony female, crossed a forked male, we got all wild type. Took those wild types together, and we expect this for each gene independently, and then we multiplied all those together. So 1/2 times 3/4. Probably should have done that in fourths. So we're going to change this to 6/16. I'm going to change this to 2/16, just so they're all the same. Let's make sure they add up. 6 plus 2 is 8. Plus 4 plus 4 is 16. So what we expect is 6 to 2 to 3 to 1 to 3 to 1. So it's a little bit crazy. Let's test that out. All right, so we got a lot of different things. Send the data to the computer, analyze results, and let's test it out. So we expected 6 wild type females and wild type males 3. Forked males 3. Ebony female 2. No, I'm not liking my hypothesis here. Well, maybe 2. What was the other one? Ebony female. Next is forked ebony male. Forked ebony male was 1. And so the last one I keep forgetting, just ebony male. Ebony male is another one. All right, we'll see. Hope you're with me. I know it's confusing, but you just got to work through it. Test it. Got it. The old 6 to 3 to 3 to 2 to 1 to 1 ratio. The key here is it's, once you kind of go through everything, it seems pretty confusing, but just figure out what you need to do for each gene independently and then multiply them together. So I'm digging that hypothesis. Digging it, digging it, digging it. All right. It's getting to be a long video. You guys asked for it. All right. Got it. All right. So we have done ebony and star. We've done ebony and forked. Now we need to do star and forked. Now, depending on how you do the cross, you expect different things. So let's do star cross to forked. So now we're bringing in two new things. We know that star is autosomal and has to be heterozygous. We know that fork is X-linked. We'll do this one the easy way, just to make my life easier so I don't have to do quite as much stuff. So let's take a forked female. All right. And let's take a star male. So for forked, we expect wild type females. This is always the easier way to do sex-linked genes. So we expect 1/2 the flies in the F1 to be wild type females, and 1/2 to be forked males. Of these, 1/2 will be star, and 1/2 will be wild type for star. So what we want to do is we want to take a star female, which is going to be heterozygous for star and heterozygous for forked. Cross that to a star male, right? So if we were doing star by itself, we'd want to do star across to star because we know that star is heterozygous, and we want to do two heterozygotes. We know that the female is heterozygous for forked, so she's going to be, we'll say a big F and a little, well, we'll do it one more time. She's heterozygous for forked. Next time I'm bringing my pen. I don't know what happened to it. I had it. And the male, what's the male? The male is forked. And he's got a Y. Why does he have a Y? Because he's a male. Or maybe why is he a male? Because he has a Y. But sex determination is a little bit weird in for flies. All right, so that's craziness. All right, so that's what we expect. Forked female. I'm going to write this down. So we're going to do a forked female across to a star male. We expect 1/2 star, 1/2 wild type, and 1/2 forked, whatever. We're going to take a star female and a star male. This male is going to be also forked. We're going to make them together. Now remember, what we expect is 2/3 star, 1/3 wild type. And then what we also expected for forked, when we did it this way, is we got 1/2 forked and 1/2 wild type, regardless of sex. So then we're doing forked a different way. We're taking forked female across to a wild type male, and we see the difference in the F1. Now this is the F2. We're taking our F1 cross, and we're doing an F2, and we're seeing, now we get 2/3, 1/3, and then we get 1/2, 1/2. So what do we expect? And sex is no longer an issue in the F2. So let me do it this way. So we can multiply these together. So now we can ignore sex. All right, so now we expect 2/3 times 1/2 star forked 2/3 times 1/2 just star. 1/3 times 1/2 just forked. And 1/3 times 1/2 wild type. So this equals 2/6. 2/6. That's not enough sixth. One-third times 1/2 is 1/6. Oh yeah, it is 1/6. 1/6. All right, you'll have to make sure you have all this sorted out, but let's test it out. All right, what are we doing? Real quick now, we're gonna cross a forked female cross to a star male. We ran out of room. So whenever you want to do something with sex linkage, make the female the mutant. It just makes life easier. Forked female, star male, check out. Sword flies. Notice the females are all wild type for forked. The males are all forked, and then half of the flies are star, and the other half are wild type. So they are wild type. But we want to take the star female and the star male, but the star male is also forked because all the males are forked. All right, and we said that we could ignore males and females because in the second generation, so remember when we do the sex-linked trait in this direction, so it's one of the reciprocal crosses, took a forked female crossed to a wild-type male. In the first generation, it's all the females are forked. All the females are wild-type, all the males are forked. So the difference shows up there. The next generation, you just get half forked and half wild-type. So there's no difference in the sex. All right, so let's test this out. I wrote it down this time. We expect, oh, I did not write it down. Let's go back and look. What do we expect? 2 to 2 to 1 to 1. This is not giving us that. These are 1 to 1 to 1 to 1, I think. Oh, let's see what we get. 2 star forked. So 2 star forked. Two just star. 1 just forked. And 1 wild type. Alright, so just star was 2. Just forked, yeah, this isn't going to work out, was 1. Forked star was 2. And wild type was 1. Test it. 0. 131. Biggest chi-square we got already. So I screwed something up. Let's try it again. we should get 2/3 star to 1/3 wild type. 2/3 star, 1/3 wild type. And our females are heterozygous for forked. Our males are forked. We should get 1 to 1 to 1 to 1. We should get 1/2 and 1/2. 1/2 wild type, 1/2 forked. So we should get 2/6 star. We should get 2/6 star forked. We should get 1/6 wild type and 1/6 forked. I don't know, man. I think we're forked. Let's do it one more time. I was looking for an opportunity to use the I think we're forked joke. Let's do it quick. See how quick we can do it. Order the flies. Female. Let's make her forked. Male. Let's make him star. Forked female. Star male. Check out. Let's make sure we use a star female. And a star male. All right, that looks better. I messed something up last time. All right, so we said this was going to be 2, 2 to 1 to 1. Test the hypothesis. Low chi-square statistic, high probability over 0.05. Lo and behold, our predictions held up. Couldn't be simpler. I'm going to challenge that notion. I believe it could be simpler. But that's the way it is. All right, so that's a lot. But it's only 3. It's not really all that much. It's just, write it out. Make sure you know what's going on paper first. Make sure you know what's going on with each gene individually first. And be able to predict what the different things are when you put them together. There was a problem, I think it was problem 38 in the back of the book that does this, and there was one of the problems in chapter 4 on the end of chapter problems on Launchpad had these different reciprocal crosses, and I think it was singed and something else. So you should be able to find these kinds of examples. And so what these kinds of examples are is taking one gene that's showing weird inheritance patterns by itself, another one that's showing weird inheritance patterns by itself, and then predicting what you get out from a dihybrid cross using both of them, and you can predict those things. You just need to take into account the weirdness that's going on with each gene. And then as long as independent assortment is occurring, you can just multiply different probabilities together to predict the outcome of various crosses. So that's the whole idea here. It's pretty complicated. But hopefully you guys are getting it. All right, so I'm going to leave it at that. I don't know that I don't know if I covered every single cross. Work on it, and if you get in the midst of it and it's too crazy, just let me know. It's more important that you do this and get it than anything else. So once you get this, so don't feel bad that if it's hard at first. That's okay. It's supposed to be hard at first, and then once you get it, then you're making some progress. You're actually starting to think like a geneticist when you can put all this stuff together, and so that's pretty cool. So all right, good luck. I should be available for the most part, so let me know.